I can hear you.
There she is. Give her applause, everybody.
Thumbs up. See my thumbs up. Woo. Hold on, let's give you a double thumbs up.
Yep.
We can hear you.
Got ya.
No, everyone's. Oh, I'm giving actual thumbs up.
Right.
You guys.
Well, I can't hear you, so that's great. I'll just start talking anyway. All right. So today we're going to talk about learning about industrial control system security. And it's an interesting topic for a lot of people for a lot of different reasons. First of all, it's an up-and-coming area of security where there hasn't been a lot of work or a lot of research done, which is unfortunate.
Yep.
All right.
Sorry about all the technical troubles.
Okay.
Thanks for bearing
Sorry,
with us,
guys.
everybody.
Sorry, guys. Good to see you. Look at all this crowd of little avatars doing things. So, hi. My name is Lesley Carhart. I, otherwise known as Hacks for Pancakes. I work in digital forensics and incident response. And I've been doing that professionally in non-standard, mostly industrial and aviation spaces for about 12 years. I work for a company called Dragos, which specializes in industrial control systems. And in my free time, I'm a martial artist. I do competitive pistol shooting. I blog a lot, and I tweet way too much. So that's who I am, I guess. So why are we going to talk about industrial control system security today? Well, because it's a really important field for us for a lot of reasons. I'll talk about why some of those reasons are. And I'm glad that you're all here wanting to learn more about it. And I know that a lot of you have just heard about industrial control system being an important part of our infrastructure in society and a good place to work because there's a lot of work to be done in it. But when you come up to me and you say, I want to learn about ICS, it's pretty much the same as somebody coming up to you and saying, I want to learn to do cybersecurity, which is like a really, really broad topic that people spend their entire life studying a single niche of. So my next question is, well, what do you want to do? It can be a little bit overwhelming to try to grasp holistically all of industrial control system security. So let's talk about some places to start and how you can learn a little bit more about the topic. So what actually is an industrial control system? Well, first of all, the immediate thought that's coming to a lot of your heads right now is that industrial control systems are digital systems. They are things that run on computers, and that's not true. They don't even have to be electronic systems. An industrial control system is simply an automated thing that causes a process to happen in an industrial environment. Technically, if you talk about gears and wheels and weights and stuff, industrial control systems have really been around since like the ancient Greeks. And over time, especially since the Industrial Revolution, they've gotten more and more sophisticated. That does not, however, mean that there aren't still analog systems and mechanical systems that are important parts of our industrial control systems. And if you want to learn about industrial control systems, you're going to have to understand what those do too. They're super important to the systems. They impact how attacks work. They impact how defense works. So we have to care about all those different types of industrial control systems because they all still exist. And I'm talking about processes. So let's define processes really fast. In an industrial context, when I talk about a process, I'm talking about something that is made to happen in an organized way, mechanically or kinetically. So it could be anything from water coming out of a pipe to tuna canning. That's my favorite example is tuna canning plants. So yeah, it could be any of those things. You put some inputs into this process and you get an output, which is usually a physical thing. It's temperature changing, it's something opening, something closing, something going down an assembly line. You can have processes inside processes. You can have systems of systems. So if you're talking about our tuna canning plant, well, you have the conveyor belt that carries the tuna, you have the canning process, you have all those little processes that become one big process, which is getting tuna fish into cans and sealed safely. And so what does a modern industrial control system actually look like? Well, usually they're pretty complicated. They don't have to be complicated. There are simple industrial control processes, and we're going to talk about one momentarily that's pretty gosh darn simple. And industrial control systems are made up of control loops. And we'll talk a little bit about what a control loop is, because that's an important concept for all of you as well. But what you really need to understand about them at a very basic level is that they're a system of systems. There are multiple control loops, systems that are supported and timed with other systems, and they contain multiple layers of stuff that we have to understand as security professionals. So different layers of technology, mechanical stuff, electronic stuff, analog stuff. Also things like protocols, network protocols, and communications methods. They're piles of those things on top of other things that make those processes happen. So let's talk about a super duper simple control loop. Now I know that we've all been stuck inside for a while now, and nobody's been to like a hotel or an airport for a little while. So let's think back to the before time. Let's go back in the bus to the before time when we used to have something called revolving doors. Now, if any of you have forgotten what a revolving door is over the last month, they are a door that you typically see in a store or a airport or a hotel. They're this big round thing, and you walk inside it, and it starts moving. And then you get out of it, and it stops moving. Very exciting technology from the before time. And so let's think a little bit more about this process. This is a super duper simple process. We have something mechanical happening, right? So we have an input, which is a human being, and an output, which is the door turning, yes, and the person getting out the other side. This is a process. And what does this door do? So we walk into the door and it turns, but that's not magic, right? It's not magic. We know that we're not turning the door, hopefully. We're not pushing it. So there's a motor in it somewhere, right? And it does some other things, though. It doesn't just turn. It does some other things we don't often think about until they go wrong. Like, have you ever gotten too close to the door and it stops turning and you're like, what the hell? This is really annoying. So that happens. And then if there's a fire, if the fire alarm goes off in the building, those doors swing open and you can just push them open and get out of the building really fast. And so it's doing some things to check for obstructions. It's doing things to check for potential safety considerations. The motor knows to go off if there's a fire alarm. So there's more going on here than just a dumb motor making the door spin. So something has to be making these decisions, right? Yeah? Okay. So what is a control loop? So a control loop in any industrial process, it could be tune-up canning, it could be power generation, it could be water coming out of your pipes in your house, it could be anything that's like these kinetic things that occur in a process. And any control loop is made up of 3 parts, okay? So we have an actuator. That's a simple part. The actuator is the thing that controls stuff like motors. That's the thing that makes the physical thing happen. It makes the valve open. It makes the temperature change, etc., etc., etc. The actuator is the thing that makes that happen. So that's easy, right? It's the motor inside this revolving door that's making a turn. And then we have to know that somebody's in the door, right? Yeah, you all with me? Okay, cool. So you have to have a sensor too, and usually that's like a motion sensor in the door. So it's looking for a person, right? And so that's pretty straightforward. But you can't just have those 2 things together. Like that's not enough, because this door is making other decisions. It's deciding that there's somebody stuck in it, something in its way, that there's a fire and it needs to open the door. So you also have a controller, and the controller is a computer. It's a computer system. Now, like I mentioned, in industrial control systems, it doesn't have to be a computer. It can be a series of gears and pulleys and elaborate steampunk stuff that makes the same thing happen. But in the case of our door, it's usually a computer. And this controller is programmed with very simple logic. 1980s stuff. It's usually ladder logic controlling these devices. So it's simple decision-making trees. And it knows it's been programmed to do certain things given certain inputs. So if somebody walks into the door, the sensor is pulled by the controller, and the controller pulls the sensor every few seconds or second, and it says, is there somebody in the door? And if the sensor says yes, the state is now there's somebody in the door, it's going to make this actuator make the door turn. But before that, it does some other checks in its logic. It says, is there anything obstructing the actuator? So it pulls the actuator. It asks the actuator, is there something in the door? Is it safe to turn right now? So it's asked. There's bidirectional communication there between the actuator and the controller, because the controller is telling the motor in the door to turn, but it's also receiving feedback about the motor saying there's something jammed in me. I can't turn right now. I need to stop. And then the motion sensor eventually is going to say somebody's out of the door. So this is your very simple control loop for this revolving door that we're pretty familiar with. So this is a very, very basic control loop. And all of these processes, all these industrial processes that we're talking about, are made up of tons and tons of control loops. Should the conveyor belt go forward right now? Should electrical generation turbines keep spinning? Et cetera, et cetera. And again, this is pre-made programming, simple ladder logic. They do what they've been told to do based on inputs and outputs forever and ever until they fail. So these controllers can keep running forever. They run indefinitely. No human being has to be there. As long as these are all functioning, these sensor, the motor, the actuator, the controller are functioning, the door is going to continue to turn when somebody walks in there. So yeah, no human operation involved there. And you can see how things might go wrong there if things start to fail in that control loop, but we're talking about a pretty simple process. But in reality, oh my gosh, in a real industrial process, the ones that I'm doing incident response and forensics in every day, they look a lot more like this, but like 10 times this. I just could only fit so many bubbles on a slide, okay? Yeah, so a real life process, industrial process, is dozens or hundreds of control loops. And they all have to work together. If you're talking about, let's go back to my favorite example, which is a tuna canning. And I don't know anything about tuna canning, so I use this example because I spend lots of time in electrical generation and oil and gas. I know how refining works. I know how crude extraction works. I can talk about all those processes, but they're really complicated and really boring. So I'm going to talk about something that we can all visualize, which is putting cans of tuna on the shelves. So you have your tuna plant, and you have to go from chunks of tuna to that tuna going down a conveyor belt, getting dumped into cans. So the valve that dumps the tuna into the cans has to be synced up with the conveyor belt. Otherwise, you get a big mess of tuna all over your conveyor belt. And then the cans have to be sealed, and labels have to be put on them and stuff. And if you're doing that with an automated process, all those automated processes, all those control loops have to synchronize with one another. And that's where things start getting really, really interesting. So, so that's where you start to have human beings, but you can't have human beings watching things everywhere in a complex industrial process. And as we become more and more efficient with our manufacturing and more automated, we've wanted less human involvement and more automation to get things down to thin profit margins and, just managing to do things in a really fast and efficient way. And if you're talking about large-scale operations that occur across a large space, let's go back to our oil and gas example. Refineries are big. They're big places. They have a lot of parts of their processes that are gigantic, and a human being is tiny. You have to synchronize a bunch of really big equipment across a large area, and human beings can only do so much so fast. So you want to have something to synchronize all of these control loops with one another. So to tell the controllers to do something different than their default simple programming. So we have our PLCs. Let's talk about some these devices, these specific devices I'm talking about here. So our controllers, there's a few different kinds of controllers out there. There's RTUs, there's PLCs. Let's talk about a very simple one. So PLCs. PLCs are typically a ruggedized computer. I've got some of them up on the screen here. This is what a typical PLC might look like. They're ruggedized computers. They're pretty low system resource because all they do is run that simple ladder logic and have inputs and outputs. So they have inputs that may be potentially serial or Ethernet, and then they have outputs that may be just electronic signals between the sensors or between the actuators. So they have a bunch of input-output cards, and then they've got a very simple computer on them that's ruggedized and made to stand really rough conditions. And it is programmed with that simple ladder logic. But again, that's only one little control loop there. That's only one little part of our potentially very large complex process. So we want to make a bunch of these PLCs, a bunch of these little simple computers work together. So the answer is simple to us technical people. We have to have a big computer to make all the little computers work together, right? Okay, so I know where most of your minds are going right now, and you're like, oh, that's SCADA. Well, it's not. SCADA is not interchangeable with industrial control systems. Yeah, we want to have something to monitor the behavior of the PLCs. We want to synchronize all of their inputs across a large facility, but that can be a lot of different things. So yes, we can have SCADA. So SCADA is a very complex system that can operate over multiple facilities, multiple buildings, even a large geographic area. So it is talking to a bunch of different technologies, including controllers, across a bunch of different facilities, and it's synchronizing the things that are happening between them using human operator interaction and programming and sophisticated analytics, stuff like that. But SCADA isn't interchangeable with industrial control systems. We've already talked about what an industrial control system is. It's a set of control loops. It could be a single control loop. It's a PLC. It's some kind of controller, an RTU, something that is running a simple control loop with actuators and sensors. So you don't have to have SCADA. It's not in every environment. In older environments, simpler environments, you can have some things like a distributed control system. What's a distributed control system? That is just a bigger computer that coordinates all the smaller computers. So your distributed control system could run a factory. So it talks to all the different PLCs, it changes their programming, it changes how they are functioning independently, and it coordinates what's happening between them. So a distributed control system is a little bit smaller scale than SCADA. It's usually made for a single building, single facility, while SCADA can do a massive power distribution network. But in a lot of places that we go, we see DCSs. We don't see SCADA systems, and that's fine. But don't use those terms interchangeably because they're not the same thing, and you're not going to see SCADA in a vast amount of industrial networks that you work in. All right, so yes, I kind of said this already. That's fine. I don't look at my slides when I'm talking. I'm just jacking at you guys over my VR headset, so everything's fine. Field devices. So field devices are your sensors mostly and some actuators. So they are the things that are taking temperatures. They are the motion sensors. They are the things that are looking at pressure, and they're providing that sensor feedback from your control loop to your PLC and then to your DCS or your SCADA system. Yeah, it's just simple sensor data. A lot of them are just simple electric signals. They're not necessarily familiar computer protocols or TCP/IP or even running over Ethernet cables, although they can be. That's cheap, so a lot of people do it today. But they can just be a set of wires. That's fine too. HMIs. Okay, so when you are sitting on Shodan and you're looking for industrial control systems out there, that this is the thing that you run into. This is the screen that shows you everything that's happening in all those control loops. So the operators who are out there at these industrial sites and are making sure everything's working okay, they're looking over how all these control loops are working together. They're looking over how efficient their DCS is. They might be doing that through an interface to a specific controller or DCS, or looking at a SCADA interface. Really doesn't matter. They have to have some kind of interface, whether it's a set of gauges or a computer screen, to see what's going on and make sure that everything automated is still functioning properly. So we have human-machine interfaces. And in a digital context, they are usually a simple computer, usually Windows embedded based. That's pretty typical today because that's a cheap thing to develop for and to put out there. And they have a screen that shows what's going on in the process. And they may be interactive or not interactive. You can have HMIs that are just showing the status of things, or you can have HMIs that allow the operators to interact with them. It may depend on privilege level. It just really depends on how they've set up their operations. So just seeing an HMI on the internet doesn't mean that you can bring down a big operation for multiple reasons. But first of all, because not all of them are actually providing real interaction with the process. And second of all, for a lot of reasons, because these processes are very complex and there's all these mechanical things going on as well as the digital things, and analog things going on as well as the digital things that we can't necessarily see or interact with using the HMI. And yeah, so I mentioned that HMIs are frequently running on Windows systems. That makes them one of the more vulnerable part of industrial control system networks. I'll talk about a couple of other spaces where we see a lot of Windows and a lot of Windows vulnerabilities, and why that's important to us from a security context. But when we see like ransomware attacks spread through industrial networks, they're not typically infecting the PLCs. The PLCs are still doing what they were programmed to do. The PLCs will sit there and follow their ladder logic until the end of time. The DCSs often don't run Windows either. The things that are issuing the overarching commands. They are ruggedized computers running proprietary operating systems too. So the ransomware isn't typically hitting them. The ransomware is hitting things like the higher level devices like the HMIs, which sucks because then you can't see what's going on in your network if you don't have an operator in there looking at valves and switches and alert lights and stuff. So you have what we call a loss of visibility, which is a concern for operators. So that's bad, but it doesn't mean things are exploding right away. It means that you just don't know what's going on as well. And that can be a risk tolerance thing where the operators say, okay, we got to shut down because we can't see what's going on anymore, or we can't impact it. If they use the HMIs to make changes and they don't have an alternative, they might say, well, we have a loss of control. We have a loss of human control over this process. It doesn't mean that things are going to explode this hour or in a day or in a week, but we have some risk tolerance that we've established in advance for our industrial environment, and that is what we allow. We don't want to exceed that level of risk. We also have safety instrumentation systems. So there's a lot of safety controls in industrial networks for obvious reasons. We're dealing with stuff that explodes, and it's not just the rotating door that's going to slam in your face. It's like things catching on fire and people dying, really bad stuff, especially in dealing with volatile chemicals and high electricity. There's a lot of safety concerns. So we have lots of safety controls in our industrial networks, and some of them are mechanical. Some of them you can't see on Shoda. You can hit all the buttons you want, and the pressure valve simply will not allow the system to explode. But there's also electronic safety controls like safety instrumentation systems. And those are usually things that can tell the process to shut down. If there is an unsafe condition, if the computer, the safety instrumentation system thinks there's going to be a fire, or there's danger to the operator or danger to the facility, they have the power to shut down the system. And they can be a security concern for a number of reasons. We've seen adversaries attack them before for twofold reasons. First of all, that's a great way to kill an operator. If there's no mechanical safety control that will protect them, and you can tell the safety instrumentation system that everything's okay, well, you've just removed a safety control and you put the operators or the public at risk. But on the other hand, they're also this giant electronic network box that can shut off the process ungracefully. So that's super bad for obvious reasons as well. And we have historians. Historians are the other place where we typically see Windows, often SQL servers in industrial environments. So they are receiving a bunch of data from usually DCSs, data systems, maybe individual controllers. It depends on how the network's set up in the vendor. And they collect lots and lots of data. They collect operational data, not security data. They say this valve opened at this time. This is our level of production, et cetera, et cetera. This is when an update occurred on our industrial control system controller, et cetera, et cetera. They keep a big log of that. It's usually in something like a SQL database. And that's another place where we often see Windows systems, particularly vulnerable Windows systems in industrial environments. So altogether, your industrial network that you're walking into when you're learning about industrial control system security is a big intermeshed network made up of all these different things, tons of control loops, some kind of control system like a DCS or a SCADA system. You have safety instrumentation systems. You have all kinds of different devices that interact with one another, put data on HMIs, and make this process function. Oh my gosh, and they're all running different operating systems. They're all functioning at different protocols, et cetera, et cetera. Let's talk about those protocols for a moment. So each one of those devices, so think about those devices we've talked about. So you have your sensors, your field devices that are receiving data, and maybe they send data back over serial to your PLC. But your PLC has to talk to other stuff. It has to maybe send data to a DCS, and it's going to do that over some kind of industrial protocol. And the DCS has to put data up on HMI so that your operators can see what's going on. And that's a Windows system, so there's a different set of protocols there. And you've got protocols on top of protocols on top of protocols making this all run. They're different between all these different devices. And I'll tell you right off the bat, in industrial spaces, availability is king. The system not exploding is king. The commands being issued at the right time to the controllers is king. So almost none of those protocols implement any sort of security or encryption by default. And that's for a reason, because again, the priority is making sure that things don't explode, that when the safety instrumentation system needs to shut off the power, it can do that quickly. When these devices are coordinated microsecond tasks in an assembly line, that they don't fall out of sync. So we can't add a bunch of overhead to these protocols. They have to be really simple and functional. And here's some protocols. This is a good snapshot moment for you guys. Here's some protocols that are very, very common that we deal with all the time. There are thousands of industrial protocols out there. It's a never-ending battle for us in an industrial-specific company to discover new protocols and dissect them. Wireshark actually does a really, really good job of common industrial protocol dissection. So if you want to delve into packet captures of industrial networks, Wireshark is a great tool to start with because it can handle a lot of these very common protocols like Modbus and DMP3, OPC, etc. You should be able to, as you're getting involved in industrial control systems, recognize some of these common ports. Like things like Modbus are just all over the place. They've been around forever. Modbus was developed in the 70s, and we still use it all over the place today. Yeah, very simple protocols. A lot of the common ones are really, really well documented, but then we have lots and lots of thousands of obscure protocols that are used in, unusual environments. They're used in, obscure vendors from 30 years ago, or a vendor that wants to keep everything proprietary, or a very specific vertical, like there's a niche biotechnology market. So we will never stop running into new protocols that we have to dissect, and that's the area where a lot of research needs to be done. And to understand how this all fits together, we have something called the Purdue model. And the Purdue model, like all models, like the OSI model, like every model we use in network engineering and security, et cetera, is a model. It's educational. It's not accurate to every situation. And there's a lot of contention right now about using these models like the Purdue model in industrial spaces. And yeah, it's not going to be perfect everywhere you go. In fact, most environments will vary a little bit from this model, but we use it to understand how things fit together. It's educational. It helps us understand how all these devices fit together. So let me walk through it really quick, because you need to know this is common verbiage. Anybody in industrial control system security knows the Purdue model. So at the very bottom of our Purdue model, so the level 0 devices are very simple electronic and analog devices like our sensors and our relays. So simple, almost dumb devices that are just getting inputs and outputs, maybe electronically. Above that, we have our simple control devices like our PLCs. So our PLCs are just simple computers. They just have some ladder logic programming. They make simple decisions. Then above that, they talk to your supervisory level, level 2, where you have your HMIs, where your operators sit. So we start having things that are more like familiar computers here. Your alert and your alarm systems. Your operator workstations, where they perform maintenance on these devices and update firmware, update programming, etc. And above that, we have our operations network, where we have our more sophisticated computing devices, even things like VMs, where we do reporting, we do historian data, We have analysis and support systems that are doing metrics. That's all happening at level 3. So again, even more familiar computer systems there. And then hopefully, we have some kind of DMZ. That doesn't always happen. There's often like people putting direct connections into their operator workstations. There's environments like manufacturing centers where there's absolutely no DMZ and no segmentation, and I find Fitbits on the industrial network. But in an ideal world, we have some kind of DMZ at level 3.5, and that separates what you would consider like your facility IT network, your enterprise network, from your OT or your industrial network. And usually it's a firewall or a couple firewalls. There's pass-throughs through it though, because people have to be able to access their industrial data. They also have to be able to like issue updates and patches and antivirus definitions to their industrial systems. So there's a bunch of pass-throughs through that firewall. And depending on the quality of security environment, that might be a good firewall configuration or a really ugly one full of holes. We see it all. And then above that at level 4, that's your normal computers that are in the facility, your ones you're checking email on, the ones you're going on the internet on, what you consider your IT or your enterprise network, going up into your corporate environment. So that's the Purdue model, and it's important to understand. But between each one of those levels that we talk about in the Purdue model, there's different protocols, there's different devices types in each level, and we have to deal with all of those in industrial control system security. This is one factory or one facility. And in that, we have a bunch of levels of different protocols and different devices. And as a security professional in that one vertical, I have to be able to understand all of those different types of devices and all those different protocols, because they're all relevant to my holistic security in the environment. If somebody's going to tamper with my PLC, they're probably going to do it through like a level 3 or a level 2 device, but there's going to have to be a pass through to the bad guy somewhere, whether they're on the corporate network or on the internet. So there's another level involved there. So I need to be able to understand a bunch of different levels in the Purdue model to understand how somebody's influencing something at level 0 or level 1. So why do I want to get you all into ICS? This sounds really intense. This sounds like a lot of work. So why do I want to get you all there? Because there are no consequences in cybersecurity like industrial control system security consequences. And what we care about most is consequences in industrial control systems, because that is the building exploding, somebody dying, somebody getting contaminated, getting sick, process failures that impact production for large areas, water not coming through your pipes at home, the power going out, etc. That's why we care about consequences in industrial control system security. We don't care that the entire network's infected with Conficker if it doesn't cause one of these consequences, if it can't cause one of these consequences. We care about things that result in horrible, horrible things happening to you and me and the operators and the facilities, et cetera, et cetera. This is all kinetic things that you can understand, that you see happen due to, maybe non-cyber reasons in real life. It's horrendous. So that's why we need you, because we want to prevent these horrible consequences from happening. And we're facing a lot of challenges. We're facing a lot of challenges in industrial control system security. First of all, nobody wants to learn it because it's a bunch of legacy systems and, boring protocols. And well, they think so. I think it's really interesting. But there's almost nobody out there who specializes in both IT cybersecurity and OT operations. They're both huge niches, and it's hard to find people who know both or are willing to learn both to a comprehensive level. And it's key to put IT technology in OT environments. So we're seeing more and more IT technologies in OT environments. We're seeing things like the cloud being deployed into OT. We're seeing lots of virtualization. We're seeing more and more of what used to be electronic communications that couldn't be intercepted, simple two-wire communications, being replaced with Ethernet cables because it's cheaper to encapsulate them and send them across the facility that way. So we're seeing more and more of these technologies that there's no security context for in the operational environment. And the adversaries are getting more and more intense. We track a lot of threat intelligence about industrial adversaries. So I break things out usually into like insiders, advanced threats, and commodity threats in industrial systems. And we're seeing all three increasing drastically. The barrier to entry into industrial attacks is lowering as more IT systems are deployed and as people have more and more time to spend doing reconnaissance of these systems and understanding how they work. We were relying very much on security through obscurity in industrial control systems because they're complicated. They're hard to understand. Adversaries have to spend a lot of time and resources understanding how to make something bad happen to them. But that's decreasing because they are out there doing reconnaissance. They have been for years now, and understanding how our infrastructure works and how to tamper with it. They're putting a lot of resources into that. So we really, really, really need more people who are conducting security research and threat intelligence in this space. And it's really overwhelming. When you're like, I want to learn industrial control system security, you're like, holy cow, this is a huge space. How am I going to learn all these layers? How am I going to learn all these devices? Well, much like I would advise somebody who wants to learn cybersecurity, I'd suggest that you break it down into somewhere where you're going to start. And that could be, I would suggest you pick some of these categories because industrial control systems are as big a space, or if not bigger, than cybersecurity. And in cybersecurity, we have to specialize in niches. So start somewhere. Figure out whether you want to focus on red team, blue team, or just security research in industrial control systems. So probably where you're focusing now. And then pick a vertical. Do you want to look at electrical power that uses totally different protocols and devices than manufacturing? Or do you want to look at oil and gas that uses yet different devices and different protocols? So start in a vertical and maybe focus down to a vendor. Maybe if you're in electrical systems, you want to focus on like Schneider or SEL or something. Pick your facility of interest and focus on a vendor if possible. And you can also focus down to a protocol. Maybe you just want to do research on DNP3. That's fine. I still say that you should focus on like a vertical maybe, but pick a protocol and reverse engineer that protocol and look at how it functions. So break it down like you would with cybersecurity. Pick an area of focus. And the good news, there's lots of familiar technologies in industrial control systems. So don't worry too much about those level 0 devices that you really don't understand yet. You need to understand how they function. You need to understand the process as a whole. But you can still do valuable security research in industrial by simply understanding the process at a high level, the consequences of concern, and then looking at the higher level devices in the Purdue model. So the things that look more like Windows computers or Linux computers that we're familiar with. And we still have a kill chain in industrial control systems. We have a separate kill chain. We call it the ICS kill chain. And it's basically the familiar IT cybersecurity kill chain on one side with a second kill chain on the other side. Because most adversaries who are attacking an industrial network, they have to intrude through the IT network. They have to intrude through higher level infrastructure to get into OT or the operational network. So typically in that kill chain, again, model's just a model. You see the adversary coming in through a IT network or a IT type connection into a higher level device, then working their way down the Purdue model into the OT devices. So that's a lot of detection points. That's a lot of places to catch an adversary if you know what to look for in terms of protocols and how the system functions, potential consequences, etc. So a lot of your traditional cybersecurity training is applicable here. You're still going to need to do memory forensics. You're still going to need to understand protocol dissection and analyze the packet captures. That's still applicable. But I want to caution you that there are substantial differences. Again, let's come back to consequences. I want you to remember the word consequences out of this talk because consequences are king. They are the be-all, end-all in industrial systems. If it works, it goes in an industrial environment. Again, we're not building security into industrial protocols for a reason, because if we make our protocols too heavy and too complex, then we start introducing delays and more potential points of failure. We want to keep things from exploding. We want to keep our process operating safely. And we have to function in that environment as industrial control system security specialists. And we have a lot of concerns due to the differences in function and these concerns about consequences in industrial networks. There are a lot of legacy systems. So you're working with a lot of 1990s and early aughts technologies. And that's for a reason, because if you go out to a vendor today and you say, I want to buy a power plant, They will sell you, it's like IBM in the 70s. They will sell you a power plant. It comes with your HMIs and your DCSs, your field devices, and it comes with all of those different levels of the Purdue model. And they all function together. They're all designed to function together. And they come with a service contract too. And if you start messing with those devices, you either don't have a system that can support another device anymore, like maybe your PLCs can no longer talk to a computer that's been updated to Windows 10, or you lose your support contract. And your vendor says, you modified our system, we will no longer support your 30-year support contract on your power plant. And you have to buy another multi-billion-dollar power plant. That's why we have a bunch of legacy systems. It's not laziness in industrial control systems. It's because we care about consequences, and we care about making sure that the systems keep functioning together and they're still under support and that people are safe. There are very few downtime windows in industrial networks. In many operations, they bring down their systems for maintenance once a year, maybe twice a year. And that's the only time you can do major system modification or maintenance. So even if you're gonna install a security patch, you're probably not gonna do it for 6 months, because bringing your facility down causes a risk to the operators, it brings down production, it has a huge risk impact. So again, people are making risk management decisions. Scanning. Do you bring down an industrial network by scanning it? Well, you can. Especially as we get to lower level devices that have been tacked into Ethernet. You know, you're talking about encapsulating older protocols into Ethernet. We run into like not fully implemented TCP/IP stacks, things that can't handle like connections being opened and not closed, et cetera, et cetera. So yes, you can break things in an industrial network by doing simple lookups and scanning. Not always. There's a lot of tolerant modern environments where you'll be okay, but we don't do it because we don't know. And again, we're talking about consequences, major physical consequences. So when we're doing vulnerability assessments and scanning, we're normally doing that during those outage windows, those rare outage windows, or we're doing it to systems in a lab that are similar to the ones in the real environment. Otherwise, a lot of our work has to be passive off span ports and taps, et cetera. It's tough. It's a different set of concerns. Yeah, I talked about the support contracts. It's easy to lose your support contract on your industrial devices if you tamper with too much stuff. And there are safety and access concerns. If you want to go out to an oil rig to replace a computer, you have to go to water survival school. You have to be dropped into a NASA-sized pool in a upside-down helicopter frame and swim your way out. That's to go replace a computer on an oil rig. Like, there's safety concerns in every industrial facility you'll go to. You'll have to go through safety briefings and have proper personal protective equipment before you walk in the door. So there's a lot more concerns there. Systems can be hard access. They can be legacy systems with interfaces that you don't have cables for. There's a lot of concerns that go along with these industrial environments that you don't normally see in IT. And even though there's a lot of concerns here, and I told you that there are ways that you can contribute right now, we really need you. There is so much research to do in the industrial control system space once you understand these caveats, once you understand the perspective of consequences and risk management that the operators have. There will never be an end to new industrial devices needing investigation and analysis, or protocols that need dissection. There are so many verticals, so many industrial devices out there in the world keeping our society running. And the threats are increasing constantly. All three types of threats I talked about. So insiders, advanced types of threats, nation state type attacks, and also commodity, like ransomware attacks, are increasing in these industrial environments. And they're increasingly connected too. Like I said, it's cheaper to put things on IT than, coax or serial cables, etc. It's cheaper to run things over Ethernet. It's cheaper to put systems in the cloud or virtualize them. So all these IT technologies are going to keep popping up in industrial control systems, and the operators aren't used to securing them. So they have their concerns about consequences, but they don't always understand how the IT system can cause those consequences, and we have to evaluate that carefully and help them use their knowledge and our knowledge to understand how those systems could cause negative consequences. So we really need more people studying this stuff drastically right now. And some resources to learn more about industrial control systems and industrial control system security. So for informal resources, there are a lot of talks and white papers out there. The vendors that do industrial control system security, both ICS vendors and security vendors have a lot of white papers and talks out there. So there's a lot of research underway already that just needs more hands. Protocol documentation. If you want to go study Modbus, there's endless documentations on how Modbus works out there. You can go be an expert on Modbus today, or DNP3, or OPC. You can go become an expert on one of those protocols and find like sample packet captures to look at today. They're pretty simple for a reason, so that they don't make things explode. You can buy a lot of ICS equipment, including pre-made trainer sets on eBay, a lot of used stuff. That can be pricey and difficult to set up at home, but if you really want to dig into things, you can certainly do that. Shodan. Well, Shodan's an interesting place to do OSINT, to understand what's out there and how things are configured. I will caution you not to poke at things. You just don't know what's going to happen. 99 out of 100 times, poking at things that are up on Shodan, like HMIs, will do nothing because of other safety controls and operator controls. But that 1%, you could be doing something really, really terrible to a process environment. And again, remember those consequences we talked about. OSINT. Even for vendors that are super secret about their devices, people love to dump like manuals for industrial devices and protocols on things like Scripty. Google hacking is a great tool too to find out how systems are configured in a lot of environments, look at their manuals to see their security specifications, etc. So there's a lot of free resources out there. For formal training, there's not a ton of formal resources out there. INL has a bunch of short videos up on their website, inl.gov. They also have formal classes, but they're kind of hard to get into. But they have just videos that you can watch that teach you a lot of important factoids about industrial control system security. And SANS has a class. They have multiple classes actually in industrial control system security. I think are pretty good. We teach a class as well at Dragos. I actually am one of the instructors of that course, so I won't talk it up too much, but it's out there. So I will open up to questions. I know we've only got a couple minutes, so please forward me some questions, and I will talk until they kick me out of here.
All right, we actually only have about 5 minutes to get the next space ready to go. So thank you everybody for joining, and thank you Lesley for talking. I apologize for the technical issues on our side. Thanks for bearing with us while we were getting everything set up.
Sure.
I have unmuted everybody's mic, so Lesley, if you want to stick around and answer questions one-on-one, you can do that while we get prepared.
Sure, yeah, absolutely.
Thank you for a great talk.
Thank you so much. Please don't send me messages on text because I'm getting bombarded. What's up? Can I answer any questions?
So, how did you
How did I get hacks for pancakes? It's a joke because I instead of making a bunch of money on talks and stuff, I just do a lot of community events and I make no money and I get paid in food. So it's a self-deprecating joke. Yes, questions?
Me?
I can sort of hear you.
Where's a good place to get started? Would you recommend any things to buy from eBay to break or play with?
Again, I'll go back to that slide where I talked about, oh man, if I can, where to start. You're going to need to pick like a vertical and, oh, I can't, but sorry, this interface is a little iffy, but yeah, so you're going to need to pick a vertical. You're going to need to pick like an area of study, an area of research, and focus on that. Once you know, I want to study SEL devices in the electric power space, then you're going to be looking for a specific model of SEL power equipment on eBay. But you need to make that decision first. You need to decide what vertical you're interested in, what vendor, and what you want to do. Do you want to do forensics? Do you want to look more like HMIs? Then it's just software. HMIs are just software on a Windows computer, so you can do a lot of research that way. Or do you want to look at physical devices like controllers? Then you're going to have to look at eBay and buying stuff. Again, make that decision about what you want to study first.
Okay, thank you.
Sure. Any other questions? I have all these avatars just staring at me. It's terrifying.
All right, well, thank you. Everybody give another round of applause for Lesley.
Oh, I see a hand raised there, Bill. I love the Darknet Diaries podcast on it. I think that's really wonderful. Stuxnet is like the that one famous case that everybody in ICS gets asked about, and it's a very, very interesting case study, but it's not the norm. But yeah, I like the Darknet Diaries podcast on it, and Kim Zetter's book and stuff. I mean, there's a lot of great writing about Stuxnet out there. There is a question from Razan.
Actually, Leslie, I apologize, but
yes.
we are scheduled for another talk here.
Okay.
I am very, very sorry, but what we can do is, if you don't mind hanging out, people can add you as friends, and then we can meet up with you in the after party or in the lobby area.
Yeah, just
if
send me
anybody has,
questions by text then.
Yo.
okay, great.
Thank you, guys.
We're going to go ahead and reset the space for the next set of